Welcome back. Today we're gonna discuss about mining, in particular what proof of work mining is. So let's quickly look at how to mine, how to perform mining. There are quite a few little steps. They are not too complicated. So the first one is we have to join this peer-to-peer network, the peer-to-peer network where peers are exchanging data about transactions and blocks. So we listen for transactions, and once we receive this data, we validate them. That's a very important step, which every blockchain peer or node should perform, like validation of input data. As long as you don't validate data, you shouldn't trust that data. That's critical for security. Then the second step is we listen for new blocks. And once we find a new block, we build upon that block, right? You remember each block has basically a block header. This is here the header, and the header has a pointer towards the previous block. And building upon the block means creating this new block here, which builds upon the previous valid block. Then the next thing is that we construct a block template. It's basically what I just mentioned here. It's to build upon this block. So we create a pointer and we build on that. Then we find a nonce that validates the new block. So in this block header here, if this is the header, you have like this pointer, right, to the previous block. This is one field, and then you have also a nonce, which is basically a number that you can change. And what you need to do as a miner, you take the hash of this blob of data. Okay, so you take the hash of this entire thing here, and this is what the hash of a block would be, right? The hash of a block is the hash of the block header. When we say validate validate a new block, this means that the hash here, this hash, has to be smaller than a given target value. So this is something we'll be looking into the next slides. So once we did find a block that satisfies this condition, we broadcast this block and we tell other miners. And once the other miners have accepted that block, then we receive a reward. So the reward is paid through the Coinbase transaction. So what is the Coinbase transaction again? Do you remember? The Coinbase transaction is the first transaction in the block, and it's the one that pays the block reward, right? And this is the mechanism by which a miner receives a reward, a financial reward for performing this mining. All right, so this is the high-level view of how to mine. So now let's look further into how this looks on the blockchain level. So here we have block 2 that has a list of transactions and it's pointing towards the Genesis block. We have block 3, and now if you want to find a new block, block 4, then we have to find a nonce n such that the hash of block 3 and its transactions and the nonce, so the whole hash of this has to be smaller than a given target value. And if we find a block that satisfies this condition, then we have found block number 4. So the best known approach to perform this hash here, this hash computation, is brute force. And you might remember from the first lecture, there's this property of hash function that's called puzzle friendliness. And because the hash functions that are being used here are puzzle friendly, the best known approach for solving this problem is brute force in 2 to the power of n iterations, n being the output of the hash function. So the target here controls the difficulty of how difficult it is to find a particular block, and we'll be looking at this in the next slide here. So mining difficulty. So Again, let's assume here we have this particular target. So the target says it's a hexadecimal value, right? 0x indicates hexadecimal value. And we have here a few bytes. These are set to 0. So let's assume we have here the following block 3. So we have a block 3 with a particular Merkle root, and this is a particular nonce that we have used. So we find that the hash here is 0x03EF, right? So they're 2 bytes, and they are not 0. So they don't actually correspond to the target that we are looking at, right? This is not corresponding to the target. Now, if we ditch this kind of value because we can't use it, we change the nonce here from D to E, and we find another hash. Well, this hash is still not valid. It's still not a valid target. So let's try again. So if we try this with beef here, you can see we change from D to E to F. Then we suddenly find a hash that actually exhibits 3 zeros here in its hexadecimal representation. So, and this is actually matching the target. So that's a good hash. And this means we found a good block. It's as simple as that. Finding a block means finding a hash that satisfies the target. So that's for Bitcoin. And this is how Bitcoin initially started its blockchain. It's how it still operates, and it's how most of the existing decentralized and permissionless blockchains operate. Now, how do miners receive transactions, or how does this happen on the network layer? Well, if a miner finds a block here by doing this proof of work, it will start to propagate this block in the network, as you can see here, and other peers get updated over time. And you might also notice there's kind of a delay, right? But there's a delay here between these nodes on when they receive data and when they can update their own local mining logistics. So mining is quite a profitable business, especially in countries where the costs of electricity are rather low. And you can see here, this is a chart of the how the mining power kind of evolved over time. It's been really only going up in the last years. So this is quite an interesting industry. The industry moved from first CPUs to GPUs and now to application-specific integrated circuits, whereby specialized hardware is being used to perform as many hash operations as possible. So it's really a race between the different miners. We observe that the majority of the mining power is actually in Asia Pacific. A substantial amount is in North America, and quite a small amount is in Europe, probably due to labor and electricity costs. If you watch a few mining documentaries or videos, there are actually quite a few online. You might see like images as such, where you have like racks and a lot of machines with a lot of coolers, and it's probably quite noisy in there. So now, one of the interesting things is that in mining pools is that you're quite unlikely to win alone this game, because in Bitcoin, for instance, you only find the block every 10 minutes, and so if there are like 100 miners, then and the likelihood for you to find the block, I mean, the variance in the payout for you is quite high. Variance meaning you might have to wait 6 months to get one payment. And this is not very sustainable, right? You need to have some kind of a more proportional, a more regular payout, just like your salary, for instance. And you still want that your payout is done proportional to your work. And this is where mining pools come into play. And they're quite interesting constructs. So you can see here, this is a mining pool distribution. It's a typical distribution for Bitcoin, where you have normally the top 3 miners together, mining pools together, actually occupy more than 50%, right? Which is dangerous if they would collude from a security perspective. But this is kind of the distributions that we have seen over the last years. So if you were to start mining and you're just a small miner, you can unite in a mining pool, you can join a mining pool, and then you can you get a proportional payout to the work that you perform. So here is another distribution for Ethereum. You can see it is probably even a bit more centralized. So Ethermine being the biggest pool, and there are a lot of smaller pools as well. So as I mentioned, right, the probability of finding a block alone is very small. So if you look, for example, at the End Miner here, this was a miner at the time that you could buy for like $480. You can go to some mining calculator website and calculate how much it would cost you. When would you break even under the assumption that the Bitcoin difficulty doesn't change much or is changing according to a specific amount that you specify. So just to provide you with a more concrete example how a mining pool operates. So you have this pool operator and you have a few pool members. And the pool members, they provide solutions to the pool operator and they get paid in proportion to those shares. Now, how do you solve these shares, right? I mean, how do you know how much processing power this particular miner in this mining pool has? Because in the end, you want to provide a proportional reward and you don't want anyone to cheat and to get more rewards than they actually are eligible to receive. So the trick here is to specify two difficulties. So you have the Bitcoin difficulty and you have the pool difficulty. So you can see here, we have this particular difficulty for the Bitcoin network. So there's a 0 more. This means it's more difficult, right? Because the set of outputs of the hash functions is smaller. So it's harder to find a block that satisfies this particular difficulty. So it's easier to find a block that satisfies this difficulty here, where you have only 2 zeros. So if the difficulty is smaller than the network, so we have big capital T and small t, then basically what we need to do, we need to find a block, right? And if we find one that is valid according to this rule, then the pool will accept it and will record, okay, you have this kind of, this is the share that you're computer processing. Now, if one of the pool members finds a block here that satisfies the Bitcoin network difficulty, then the transactions in this particular block that the mining pool client was operating on will be chosen by the operator. And the Merkle root also contains a Coinbase transaction that pays the pool. So it doesn't pay the miner that's participating in the pool, it pays the mining pool. And then the mining pool redistributes the reward down to its participants. Thank you very much for watching and see you in the next lecture.